Okay. Hello, everybody, and thank you for the invitation to this interesting workshop. The talk is called Multicuts, but it could also be called How to Revive Edge Detection. If we look at segmentations, there are two basic approaches. Either we can use the appearance of the objects, so the texture and color and so on, and define region properties, or we can base the segmentation on the boundaries of the object. And here in the right-hand side, this is from our own research on connectomics. I will go to that later in the talk. We only have boundaries, so the region appearance approach doesn't work in this case. Yeah, and so classic solutions, just two simple examples. We have the graph cut or grep cut, which is an extension of the graph cut, which defines a unary potential that actually describes the appearance of the object of interest and the background. And then we have pairwise potentials that act as a regularizer, and then we solve a maximum flow problem. And from the koala image, we get, for example, this segmentation. That's actually done with PowerPoint itself. So the grep-cut algorithm is built into PowerPoint, so just so that you can do this kind of segmentation quickly. And another classical solution is Kenny's algorithm, which is the edge detection variety of segmentation algorithms, where you first define a boundary indicator, typically the gradient or the eigenvectors of the Hessian matrix or something like this. And then you perform non-maxima suppression perpendicular to the boundary indicator direction, and maybe hysteresis thresholding to filter out the irrelevant edges. And then it looks like this. So the problem with this classical edge detection is that the edges usually have gaps. And here we see some of these gaps, here where the arrows are. And if you then do connected components on the non-boundary pixels, then what you end up with is usually a huge region that covers most of the image. And that's not very useful for further analysis. And there is a ton of heuristics in the literature to solve these problems, but in my opinion, none is really satisfactory, and the multicut is a more principled way to solve these problems of gaps. But before we can come to the multicut, we need to look at some older methods. One way to avoid these gaps is to use a region growing algorithm, for example, the watershed, where you here, this is the boundary indicator surface seen from the side, and then you have markers that define the regions, and then you flood the boundary indicator until the marker water meets, and that will be the watersheds corresponding to the edges. By definition, this algorithm cannot have gaps because the region growing prevents it from happening, but we have a hen and egg problem. So in order to get the regions we want, we need one marker per region, which is easiest to define if we already know the regions. And that's, of course, pretty hard. And what most people do nowadays with watersheds is not to use it as an algorithm to produce the final segmentation, but to produce watershed superpixels, which means we place more markers than regions, and then perform the region growing, and then we end up with a superset of the true boundaries if the markers were placed reasonably and the boundary indicator is good. So here, for example, these will be the superpixels that arise from the set of markers that are marked in red in the left image, right? So this is the superpixel regions, and these are the boundaries. And you see, for example, here, the upper border of the koala is a part of the superpixel boundaries. So this now reduces the task of segmentation to a two-stage procedure. So we start with superpixels, there are various ways. I showed watersheds, but there's also, for example, the slick algorithm and various others. And then in step 2, we try to identify the relevant boundaries of the superpixels and delete the irrelevant boundaries. And to do that, we define a probability for each superpixel boundary to be correct, and then we use this probability to somehow assign labels to the superpixel boundaries, where label 1 means that we want to keep the boundary, so we believe it's correct, and 0 means we want to delete it. And it has a number of advantages to do it in 2 stages. First, stage 2 is usually is always a much smaller problem than the problem on the original pixels, because the number of superpixels is maybe a hundredth or a thousandth of the number of pixels. And also, I will talk about a little bit more on the next slide, we can define more expressive features on top of superpixels. But the requirement is that the superpixels actually form an oversegmentation, so that the true boundaries are a subset of the superpixel boundaries. Otherwise, we are lost, right? If a boundary is not in the superpixel boundaries, then it doesn't work. So first, we have to define these probabilities, whether we believe that the superpixel boundary is correct or not. And I already mentioned this labeling. And these probabilities, so we have the probability that the label should be 1, given some features that we can measure from the image. And then the corresponding probability that the label should be 0 is 1 minus the other probability. So we only actually need to define 1 probability. So, and in order to define these probabilities, we can define features. So this is similar like the filters that we would use to define the original boundary indicator. But here, we are able to define these features according to the superpixel geometry. So for example, we can take the average color, not just in a circular window around the current pixel, but we can actually compute the average color over a superpixel, which is a geometrically more meaningful averaging, right? Or we can use a superpixel boundary and compute its curvature, which is not easily definable on a pixel-based level. Yeah, so that means we get very expressive features for these superpixels, and typical examples are, as I said, geometric boundary properties like length or area of the boundaries or curvature. We have intensity properties of the boundaries, like the maximum or the mean gradient magnitude along the boundary. Or we can also define region properties, and then, for example, say an edge is important if the 2 adjacent regions have very different color. Yeah? And so we collect a big number of features, so in the order of like 100 or several hundreds, and then use a machine learning algorithm in order to learn the mapping from the features to the probabilities, which is here marked in red. So when the boundary is red or reddish, then the probability for it to be correct is high. And if the boundary is greenish, then the probability for it to be removed is high. Yeah, so this is the basis for our multicut algorithm. And I will later in the talk or in the demo session show you a software demo. So now we can make the first step towards the multicut objective. We want to keep those boundaries such that the total probability of the boundaries that we keep is maximum. So in this, here we make the false assumption that all the boundaries are independent. And then the total probability is just the product of the individual probabilities. So we have the product over the edges that we keep and the product over the edges that we delete with the opposite probability, and that will give us our total probability, and then we try to maximize it by choosing the labels L, I accordingly so that we get the maximum expression. So it's easy to show that this expression can be re-expressed using the negative log odds, which is the logarithm of the ratio of these probabilities. And then this gives us edge weights, Wi, and these edge weights are negative if the boundary should be kept and are positive if the boundary should be removed. So, and then our objective here turns into a linear function of the labels. So the Li are the labels, 0 or 1, and Wi are the weights. And we want to choose the labels such that this is minimized. So that's not yet the full multicut objective because we need constraints, which I will talk about later. So now we can easily see by not even calculating what the minimum of this objective is. It's very easy. We only keep the edges, so label them 1, when the weight is negative. That gives the minimum of the expression, obviously, because whenever we choose we keep a weight that is positive, then the energy gets bigger, and we want to minimize it. So, but this doesn't solve our problem, so we end up with the same gap problem as in the beginning, because these probabilities are arising from data, so they are not perfect, and some of them are positive even if they should be negative, and the other way around. And so we again have gaps here and end up with one big region that covers all the image. So another classical solution to this problem is to use agglomerative clustering. So the goal is to prevent gaps, and agglomerative clustering prevents these gaps by design. So the algorithm is very simple. So we look for the worst edge, so that's the one with the biggest weight, and that's the one that's least likely to be correct. And then we set its label to 0, which means that we merge the adjacent regions of that edge. And then we get a new region, and then we update the weights of the remaining edges of the new region. This step is important because otherwise it would just be the same as thresholding. Yeah, and then we repeat this process until some termination criterion, and that's one of the biggest problems. There's no easy natural termination criterion. And so usually you stop at an arbitrary number of regions, for example. And the other thing is it's a greedy algorithm, so it works reasonably, but it doesn't find the global optimal solution. And so you see here, this is an example of agglomerative clustering. So here we have too many regions in the koala. But if we keep merging, then at some point the koala will be merged with the background before all the internal boundaries are deleted. That's the usual effect that we see in practice. So, and the multicut does it differently. So what would a mathematician do if things don't behave like they should? He would introduce a definition. Yeah, so just define things as they are supposed to be. And here that means we simply forbid gaps to occur. And in mathematical terms, this means we must add constraints to our objective function. And in the next slides, I'm going to show which constraints and how to derive them. To do this, we first need to change to the region adjacency graph, which is the dual graph of our boundary graph. So here is an example from connectomics, so nerve cells. So these are the regions, the different colors, and each region has a node in the region adjacency graph, and two nodes are connected by an edge if the corresponding regions share a piece of boundary. Yeah, so it's a standard, very old concept. of image processing. So, but here, the meaning of the edge labeling that changes a little bit. So I said label 1 means we want to keep a boundary, but in the region adjacency graph, this means we want to cut the dual edge. Yeah? If we want to keep the primal edge, we must cut the dual edge. And the other way around for label 0. Yeah? And then if we cut some of these edges here, then we can compute the connected components of the residual graph. And these residual graph, the connected components will then be the regions of our segmentation. So, and provided we cut the correct edges, then our connected components will actually be the desired regions. So now what has this to do with gaps? The critical observation is that gaps can be easily found in the region adjacency graph. So whenever an edge is cut, which means it has the label 1, which is here, the red edge in this example. So, and here the primal edges are the gray and the blue ones, and the dual edges are the orange and the green and the red ones, right? And so when we cut the red edge, it means that we keep the blue primal edge. So, and here we have a contour in the primal graph, so in the superpixel, and the blues are kept, and the gray one is the gap, right? And here we see when we have an edge that is cut, so the red one, and then we find a path from the two endpoints, that's the green path, that connects these and doesn't go across a blue line. Then we know there must be a gap. Yeah, is this clear? This is the most critical slide of the talk. Yeah, and in practice, you just check all the edges that are cut and find the shortest path between the endpoints using Dijkstra's algorithm. If you find no path, then everything is okay. And if you find a path, then you have a gap. To put that into mathematical terms, we see that gap detection refers to cycles in the region adjacency graph. So the green line and the red line together form a cycle in the graph. And a gap is characterized that the cycle has an edge that is cut, but a path that's not cut. And this gives rise to what's called the multicut constraints, or the cycle constraints, which can be formulated that no cycle is allowed that contains exactly one edge that is cut. Yeah, so the sum over the labels over all edges in a cycle must be not unequal to 1. If all are 0, then there is no cut edge, no problem. And if the sum is bigger than 1, then there are at least 2 cut edges, and everything is also okay. So the simplest configuration, like here, is a loose end, but there are more complicated configurations like this. Here, there's no loose end, but still we have a gap, right? So formulating that as an inequality is not so convenient mathematically. It's better to reformulate this thing as less than inequalities. So we take any edge and all the other edges in a cycle where this edge is a part of. Yeah, so LE is an edge and C is a cycle that contains I. And then if the right-hand side is 0, that means that is a path, then the left-hand side must also be 0. We can't cut it. Yeah, so that's equivalent. And if you look at this problem formulation, you see that this is a standard integer linear program, which has been topic of the optimization research for a very, very long time, and there are very good algorithms for it. Also, there are 2 severe difficulties. The problem is in p-hard, so in the worst case, it takes exponential time to find the optimal labeling. and the number of constraints. So it's exponential in the problem size because there are so many cycles in a graph. But fortunately, that's not hopeless. So the exponential complexity, first of all, there exist very good heuristics that are implemented in standard packages. So the best are the commercial ones, Cplex and Gurobi, which fortunately are free for academic use. But there are also some open source ones which are unfortunately a lot slower. And you have always to remember that NP hard means in worst case. But in practice, the worst case doesn't occur provided that our probabilities are close to correct. So we have only a few gaps. And that means if we have a good learning algorithm that's almost right, so that thresholding almost works, then the algorithm has only very few things to do and then it works quickly. So then the second problem, the exponential number of constraints, is when there are only few gaps, actually only very few of these constraints are really needed. And that means we can use the cutting plane method, which means we add the constraints on demand. So that means we first solve the optimization problem naively, but just by thresholding, so what I showed in the beginning. And then we find violated constraints, so we find the gaps, and add a constraint for each of these gaps to the problem. And then we resolve. And when we can't find any violated constraints anymore, then we know we are done. Yeah, and usually this converges quite quickly after a few rounds of adding constraints. And the nice thing is that when we add constraints, the solvers can reuse the previous iteration as an initialization, so it's getting faster and faster as we proceed. So here, the nice thing about this is that we just tell the algorithm that this solution is wrong, but we don't tell it anything about what the correct solution would be. So it can choose between, for example, closing the gap or deleting the right side and introducing another branch of the segmentation. And there are plenty of resolutions, and the algorithm is supposed to solve them all globally together, yeah, to find the global minimum. And if we look at the result, then this is the koala, or one example of the koala segmented with the multicut algorithm. So now for our real application, I have a few minutes left. So connectomics is biologists use 3D electron microscopy of animal brains at around 10 nanometer isotropic resolution, or maybe anisotropic, depends on the method. And the goal is to determine the brain's full wiring diagram. So the neurons and the synapses and who's talking to whom. Yeah, and of course, first you start with small brains like flies, and then go to bigger brains. And the method is, so one method is you picture the surface and then cut off the surface and then picture again, and then you do this for a few months and collect like several terabytes of data. So here is the raw data. So that's one slice of a big 3-dimensional data set. Here are the membranes, and this is the boundary indicator that we use to compute superpixels, and this is now computed by a neural network, which is currently the state of the art, so as good as we can do it right now. And of course, the superpixels are already quite good, and then the multicut doesn't have to do that much work. Then we define the superpixels here. You see here are some false edges, mainly here, and then we have the multicut segmentation, and this is, so for normal image processing requirements, this is very good, but for connectomics, it's not yet good enough, because if you just make a tiny mistake, you can have 500 synapses assigned to the wrong neuron, and this is still a problem. Yeah? And the neurons are huge, so it's easy to make one mistake per neuron. So we are not yet there. Here, you see it's important to have the multicut constraints. On the left, we see again all the yellow surfaces have a gap somewhere in 3D. Not necessarily in the same slice, but it is 3D, right? And a very, very tiny gap is sufficient to destroy an entire surface. And here with multicut constraints, so the blue ones are the ones that we keep and the red ones are the ones we delete. Yeah, here is some neurons that we have segmented on this basis. And here is a benchmark, the ISPI 2012 Connectomics Challenge. So we have here the results from 2012, the winner of 2012 when this challenge was first made. So it's around 95% correct. And then humans are here 99.7% or something. And you see now it's 2016 and our multicut in connection with neural networks is getting close to the humans. So in progress since 2012 is quite substantial. You also see here that the neural network alone gets us a long way, but the multicut can still improve on the mistakes in the neural network. Yeah, then I can only briefly touch this, but you have it in your printed material. So we need approximation algorithms because here for a fly brain, we have 100 terabyte of data. So 120,000 by 80,000 by 10,000 pixels. And the multicut, exact multicut only works for like maybe 1,000 cubed or 500 cubed or something like that, depending on the data. And so we can do blockwise fusion moves and cut, glue, and cut, but this is a very active area of research. And then there are a few extensions. The multi-way cut combines the edge detection with region appearance measures, like in graph cut. So, and it does this in a very similar way. So we also, for each semantic region type, we introduce an auxiliary node to the region adjacency graph, which is connected to all the others. And then we also need to find the labels of these auxiliary edges, right? And these labels are subjected to essentially the same cycle constraints as the original problem. Yeah, so this is one extension. Another is the lifted multicut, where we introduce long-range edges to the region adjacency graph, so between nodes that are not neighbors. And then they need lifted edge constraints, which are a little bit different, so that regions remain connected, so spatially connected. Otherwise, two regions could just be connected by a lifted edge. Yeah, and these lifted edges can be attractive. That means these two nodes, also they are distant from each other, want to be in the same region. Or they can be repulsive. Two nodes that are distant from each other want to be not in the same region. Yeah? So for example, repulsive could encode size constraints. So if two nodes are too far from each other, they cannot be in the same region because regions cannot be that big. That's one possibility. So, and then the perturbed multicut is we perturb the weights, the W's, randomly. And then if the segmentation changes very much, by a little perturbation, we know that this edge or this part of the segmentation is probably uncertain. Yeah? And this is also a very active area of research. Everything is open source except for these commercial solvers I mentioned. And this is our iLastic program, which in the newest version contains a new multicut workflow, which we can show later in the demo session. Yeah, and you can download this from www.ilastic.org. Yeah, so the summary is so the multicut algorithm is just a linear optimization with linear constraints and Boolean variables, so a standard ILP which can be solved with standard algorithms for reasonable problem sizes. And we should learn the weights with modern machine learning algorithms, because the better the weights, the better the algorithm converges. And as you have seen, we achieve state-of-the-art results on a challenging connectomics problem. And take-home message maybe is just prevent gaps in edge detection by simply forbidding them. Right? Yeah, so then I have a page of references so that you can read the detail, and I would like to thank you for your attention and the team for the hard work. Thank you.